Welcome to Robotics Lecture 9. This is your Professor Atif Fareed Muhammad. Let's continue where we left off. We will be looking at Introduction to Trajectory Generation. We'll look at the definition and importance in robotics of the trajectory generation. We'll also look at the overview of applications in industrial robots, autonomous vehicles, etc. in quite depth. Trajectory generation in robotics refers to the process of calculating and defining a path that robots and effector or body should follow to move from an initial position to a desired position in space. The path known as trajectory involves not only the spatial route, but also the velocity, acceleration, and time parameters that dictate how the movement should be executed. The goal is to produce smooth and efficient motion while adhering to constraints such as avoiding obstacles, minimizing energy consumption, and respecting the mechanical limits of the robot's joints and actuators. In practice, trajectory generation can be achieved through various techniques including polynomial interpolation, spline curves, and numerical optimization methods. These techniques ensure that the robot's movements are both precise and feasible, permitting it to perform tasks such as assembly, welding, or pick-and-place operations with high accuracy. Effective trajectory generation is crucial for enhancing the performance and safety of robotic systems, enabling them to operate autonomously in dynamic and complex environments. The objectives. Let's look into that in a little bit more depth. Primary objective of trajectory generation in robotics is to ensure that a robot can move efficiently and accurately from one point to another, as mentioned earlier. This involves calculating a path that not only connects the start and end points, but also optimizes the movement in terms of time and energy consumption. By defining the trajectory, robots can perform tasks more quickly and with less wear and tear on their mechanical components, thereby increasing their operational lifespan and reducing maintenance costs. Another key objective is to ensure that safety and reliability of robotics in terms of robotic operations in reality. Trajectory generation takes into account the physical limitations of the robot, such as joint limits and maximum velocities as mentioned earlier, to prevent mechanical failures or accidents. Additionally, it incorporates obstacle avoidance algorithm to navigate around potential hazards in the workspace. This is particularly important in dynamic environments where the positions of obstacles may change unpredictably, requiring a robot to adapt its trajectory in real time, such as automotive cars, which are robotic or robotaxi. Trajectory generation aims to enhance the precision and quality of task execution for applications requiring high accuracy, such as assembly lines or surgical robots. The generated trajectory must ensure that robots and effector follows a precise path with minimal deviation. This precision is crucial for tasks that involve intricate manipulations or interactions with delicate objects. By achieving these objectives, trajectory generation plays a vital role in improving the overall performance and versatility of robotic systems in various industrial and research applications. The basic concepts of trajectory generation as discussed earlier. Let's look into the definition of trajectory and path and the key differences between path and trajectory with an example. In robotics, a path is defined as a sequence of configurations or positions that a robot must follow to move from a starting point to a destination. It is essentially a geometric route that outlines where a robot should go without considering the timing or speed of the movement. For example, in the context of a robotaxi, the path could be a planned route from a pickup location to a drop-off point, including the streets and turns it needs to take to reach the destination. A trajectory, on the other hand, extends the concept of path by incorporating the time dimension. It specifies not only the route that the robotaxi, as our example, should follow, but also how it should traverse that route over time. This includes details such as the speed at which the robotaxi should travel, when it should accelerate or decelerate, and exact times it should reach specific points along the path. For instance, the trajectory of a robotaxi would include its speed profile, ensuring it stops at stop signs, slows down for turns, and arrives at the destination within the predicted time frame. The key differences between the path and trajectory lies in the inclusion of temporal information. While a path is purely spatial and provides a static route, a trajectory is dynamic, dictating how the movement should occur over time. This distinction is crucial in applications where timing is essential, such as in the autonomous vehicles that must navigate safely and effectively in real-world traffic conditions. Another important difference is the complexity and computational effort required to generate each. Path planning primarily focuses on finding a feasible route from start to finish, often using algorithms that consider spatial constraints and obstacles. Trajectory planning, however, requires additional considerations such as kinematic and dynamic constraints of the robot, environmental interactions, and real-time adjustments to ensure smooth and safe operation. In the robotaxi example, trajectory planning would involve continuously updating the speed and direction based on real-time traffic data, pedestrian movements, and other dynamic factors. The general consideration in path description. We just discussed paths versus trajectory. The constraints are velocity, acceleration, and the jerk movement that can happen. Continuity and smoothness is also a part where path description comes pretty handy for us. The path description techniques. Let's look into the overview of common techniques with importance of choosing the right technique. Path description techniques in robotics are methods used to define and represent the route that a robot should follow to navigate from one point to another. These techniques vary in complexity and application depending on the environment and the specific requirements of the task. Common techniques including waypoint navigation, grid-based methods, graph-based methods, and potential field methods. Each technique has its own set of advantages and is suited to different types of robotic applications, from simple point-to-point movement to complex navigation in dynamic environments. Waypoint navigation is one of the simplest path description techniques, where a series of points in space are defined and the robot moves from one point to the next. Grid-based method involves dividing the environment into the grid of cells, where each cell can be marked as occupied or free, permitting the robot to plan a path through the free cells. Graph-based methods, such as those using visibility graphs or Voronoi diagrams, represent the environment as a network of nodes and edges, enabling the robot to find optimal paths during or through complex spaces, or during the traversal of the complex spaces. Potential field methods use artificial potential fields to guide the robot along the path, where a robot is attracted to the goal and repelled by obstacles. Choosing the right path description technique is crucial for the efficiency and success of robotic navigation tasks. The selection depends on various factors, including the complexity of the environment, the presence of obstacles, and need for real time adaptation and computational constraints. For instance, waypoint navigation might be sufficient for a robot operating in a structured and predictable environment, while the dynamic and cluttered environment might require more sophisticated techniques like graph based methods or potential fields. The right technique ensures that the robot can navigate safely, efficiently, and reliably, ultimately enhancing its performance and effectiveness in completing tasks. Joint space schemes introduction. We'll discuss in this discussion. We'll define and basic concepts, sharing with you advantages of joint space schemes with an example. One example of a joint space scheme in robotics is the use of inverse kinematics to control a robotic arm. In this approach, the desired position and orientation of the end effector are specified, and the joint angles required to achieve this pose are calculated. For instance, consider a robotic arm used in an assembly line that needs to pick up an object and place it in a specific location. The inverse kinematics algorithm computes the necessary angles for each joint in the arm so that the end effector reaches the desired position. This joint space scheme allows to precise control of the robotic arm, ensures that it can perform tasks accurately and efficiently. In this joint space scheme, the robotic arm's movement is planned and executed by interpolating the joint angles over time, creating a smooth trajectory for each joint. This method is particularly useful in structured environments where the positions of objects and obstacles are well known. By controlling the robot in joint space, the system can optimize the movement of speed, energy, efficiency, and mechanical constraints, reducing the risk of collisions and minimizing wear on the robotic components. This approach is widely used in industrial robotics, where repeatability and precision are crucial for tasks such as welding, painting, and assembly. Now let's look into joint space trajectory planning by looking at polynomial trajectories, cubic and quintic polynomials for smooth motion. Joint space trajectory planning using polynomial trajectories is a common technique in robotics to achieve smooth and controlled motion of robotic joints. In this approach, polynomials are used to define the desired trajectory of each joint over time. For example, consider a robotic arm that needs to move from an initial position to a final position within a specific time frame. Polynomial trajectories can be designed to ensure that the arm's joints start and end at the desired position with zero velocity and acceleration, resulting in smooth and stable motion. This method is particularly useful for reducing mechanical stress and avoiding sudden jerks that can lead to vibrations or inaccuracies in the robot's movement. Cubic and quintic polynomials are frequently used for joint space trajectory planning due to their ability to provide smooth motion profiles. A cubic polynomial trajectory is defined by 4 coefficients and can satisfy boundary conditions such as initial and final positions and velocities. For instance, a cubic polynomial can be used to plan the trajectory of a single joint, ensuring that it starts and stops smoothly. However, cubic polynomials have limitations in controlling higher order derivatives such as acceleration, which can still result in abrupt changes. Quintic polynomials, on the other hand, offer more control over the motion profile by including additional coefficients to satisfy boundary conditions for position, velocity, and acceleration. This higher order polynomial ensures that the trajectory is smoother and more suitable for applications requiring precise control over the entire motion profile. For example, in a robotic arm performing a delicate assembly task, quintic polynomials can be used to plan the trajectory for each joint, ensuring that the arm moves smoothly and accurately without any sudden changes in acceleration. By using polynomial trajectories, robotic systems can achieve more reliable and efficient performance in a wide range of applications. Let's look into examples of joint space scheme where robotic arm moving from point A to point B using the joint space interpolation. We just discussed that. Let's delve a little deeper in visualization or diagram technique. In the context of Boston Dynamics robots, such as Spot, joint space schemes are crucial for achieving precise and dynamic movements. These robots utilize a combination of sensors, actuators, and advanced control algorithms to coordinate the motion of multiple joints in real time. For example, when Spot navigates uneven terrain, each leg's joint, including the hip, knee, and ankle, are controlled independently to adapt to the environment. By employing joint space scheme, the robot can calculate an optimal angles and trajectories for each joint, ensuring stability and agility. This approach allows Spot to perform complex tasks such as climbing stairs, traversing rough terrain, and even recovering from slips or falls. To visualize how joint space schemes work in Boston Dynamics robots, consider the movement of a single leg. The hip joint might rotate to position the leg forward or backward, while the knee joint bends to lift or lower the leg, and the ankle joint adjusts to maintain balance and adapt to the surface. Each joint movement is carefully coordinated using polynomial trajectories, which define how the joint angles change over time. These trajectories often are ensured the smooth and controlled motion, reducing mechanical stress and enhancing robots' overall performance. By integrating joint space scheme and real-time feedback from sensors, which comes in terms of the visualization or diagram effect, the Boston Dynamics robots can achieve remarkable level of mobility and adaptability in various environments. The Cartesian space schemes introduction, let's look into this with an example. In robotics, a Cartesian space scheme involves planning and controlling the movement of a robot and a effector in terms of Cartesian coordinates, which define its position and orientation in three-dimensional space. Unlike joint space schemes that focuses on angles and the movements of individual joints, Cartesian space schemes concentrate on the desired path and trajectory of the end effector itself. So this approach is particularly useful for the tasks that require precise manipulation and interaction with objects in the environment, such as assembly, welding, or pick and place operations. By specifying the end effector's position, velocity, and acceleration in Cartesian space, robotic systems can achieve more intuitive and task-oriented control, making it easier to program and execute complex motions in the workspace. A robot drawing a straight line between 2 points in Cartesian space is an example. Visualization of diagram has also like the three-dimensional pictorial representation that can be considered as one of the examples. Now let's look into geometric problem introduction. The geometric problem often refers to the challenges associated with planning and executing movements in a physical space while considering the geometric constraints of both the robot and its environment. This involves determining feasible paths and that avoid collisions with obstacles, optimizing the trajectory for efficiency, and ensuring that robots' mechanical limitations are respected. Let's have a little more delving in the common geometric problems. So singularities, obstacle avoidance, path planning, and cluttered environments can be considered another examples. Geometric problems can range from simple point-to-point navigation in an open space to complex manipulations in cluttered environments. Solving these problems typically require advanced algorithms and computational techniques such as path planning algorithms, geometric modeling, and spatial reasoning to enable the robot to operate autonomously and effectively in the real world. A robot navigating around obstacles using Cartesian path planning is one of the geometric problems example. Visualization of diagram in a 3D space when a robot is trying to figure out what it is, where it is heading, can be another example that you can think of. Trajectory generation algorithms. Let's look into this with a little bit more in depth. Trajectory generation algorithms are essential tools in robotics that compute the optimal path for the robot to follow. Considering various constraints such as time, velocity, and acceleration, these algorithms ensure smooth and efficient motion by generating trajectories that avoid obstacles and adhere to the mechanical limits of the robot. Common techniques include polynomial interpolation, as we discussed earlier, spline-based methods, and numerical optimization, each tailored to specific applications and environmental conditions. Joint space algorithms are inverse kinematics, trapezoidal velocity profiles. I suggest you to look into the Google Scholar in more depth to learn more about these two mentioned. Cartesian space algorithms are rapidly exploring random trees or RRT, probabilistic roadmaps or PRM. I suggest you to look into this also in Google Scholar to find a little bit more in depth as your own study at home. Practical consideration, real-time trajectory generation, as discussed earlier, needs a robot to be precise and keep accurate movements. Computational efficiency, the angles, the hip, and the movement of the ankles need computational efficiency to allow for a robot to pick one step at a time according to the terrain it is in. The case study is industrial robotics. We have discussed the applications of trajectory generations in individual settings earlier in terms of welding or picking things up and putting at another spot from point A to point B. The example here is assembly line robots in a car manufacturing facility or some other manufacturing facility where the robotics are used. These are some examples of industrial robotics. Autonomous vehicles, we have discussed extensively in earlier slides. A robotaxi utilizing the algorithms to chalk the path out from point A to point B, and that is the path planning, or self-driving cars is another example. The challenges in trajectory generation: dynamic environments, real-time constraints, computational complexity, as we have discussed in quite depth. Now let's look at future trends in machine learning in trajectory generation and adaptive and learning-based approaches with an example each. Machine learning has been increasingly applied to trajectory generation in robotics to enhance adaptability and decision-making in complex environments. One example is the use of reinforcement learning to train robotic systems to generate optimal trajectories. In this approach, a robot such as autonomous drone learns to navigate through an environment by interacting with it and receiving rewards or penalties based on its actions. Whereas adaptive and learning-based approaches in robotics leverage real-time data and machine learning techniques to enhance the decision-making and control processes of robotic systems. One example in this use of adaptive control algorithms that adjust a robot's trajectory based on feedback from sensors and environmental changes. For instance, an autonomous underwater vehicle, or AUV, equipped with adaptive controls can modify its path in response to ocean's current and unexpected obstacles, ensuring efficient and safe navigation. By continuously learning from its environment. The AUV can optimize its trajectory to achieve mission objectives such as mapping the ocean floor or inspecting underwater structures. Last but not the least, trajectory generation is a robotic arm moving smoothly from one point to another using polynomial trajectories. And this is a summarization of this entire lecture. Joint space schemes are robotic arms, joint angles, interpolated to move from an initial to a final configuration. Whereas Cartesian space schemes are robot and effector moving in a straight line in Cartesian space. Geometric problems, a robot avoiding an obstacle while moving among the Cartesian path, as discussed in quite depth. Hopefully this has given you some decent thought process to conduct research using Google Scholar or IEEE Explorer. Happy learning. See you in the next lecture.